Let's consider an example of an unforced harmonic oscillator. And I'm going to pick an example that happens to have complex eigenvalues. I hinted at what eigenvalues were last time. I'm not going to test you on complex number eigenvalues, but we can still illustrate ideas that you should understand for the exam. The general second order equation for the position of a mass in a spring is my double prime plus by prime plus ky equals 0, where these derivatives, the prime and the double prime, are with respect to time. I'm avoiding Leibniz notation because it's quicker to avoid it. M is the mass, typically in kilograms. B is the coefficient of friction. It's going to be in newtons per meter per second because it's got to cancel with this to give you units of newtons. K is the spring constant in newtons per meter. Let's go ahead and take a particular example. Let's take M to be 1, B to be 4, and K to be 13. I'm picking those numbers because it works out nicely and has complex number eigenvalues. What do we end up doing to try to solve this equation? Like we did last time, you guess. And the thing to guess is an exponential function of t, e to the rt, where r is an unknown constant. And we try to solve for r. Just like last time, we differentiate this with respect to t. There's the first derivative. Do it again to find the second derivative. Plug this into the left-hand side. What do you get when you do so? You get r squared e to the rt plus 4r e to the rt plus 13 e to the rt. I want to set that equal to 0 and see if I can solve for a value of r that will make that work. I can factor the left-hand side, factor out the e to the rt, and in parentheses, I'd be left with r squared plus 4r plus 13. Since e to the rt is never 0, the only way for this expression to always equal 0 for all t is if the coefficient of e to the rt is 0. R squared plus 4r plus 13 equals 0. So then you get all excited and say, oh, it's a quadratic equation. I know how to solve that. I'll factor it. And so you sit there for 5 minutes, 10 minutes, 15 minutes trying to factor it, and you're not successful. So then you're like, okay, I guess I have to use the quadratic formula. Negative b, which is -4. There's the b, plus or minus square root of b squared is 4 squared minus 4 times the coefficient of r squared is 1 times the constant term is 13, all divided by 2 times the coefficient of r squared. This becomes -2 plus or minus 1/2 square root of 16 minus 52, -36. And so then we give up and we say there's no answer. No, there is an answer. This differential equation can be solved, and we can use this complex number to do it. Square root of -36 can be thought of as square root of -1 times square root of positive 36. In other words, I times 6. And you can write these things then as -2 plus or minus 1/2 times 6 is 3. -2 plus or minus 3i. These two complex numbers, where I is the imaginary unit, are roots of that quadratic equation called the characteristic equation. We do call these eigenvalues. Most typically, the word eigenvalues is used with matrices and vectors. And I can actually relate this to matrices and vectors, and I do in Diff with linear. I won't bother here. It's just sort of beside the point. How do I use this? How is this possibly useful for getting a real answer? The key is Euler's identity. What we do is say, okay, I guess y equals, for example, e to the -2 plus 3i times t must be a solution of the differential equation. But it's a complex number solution. How does that have any real meaning? Well, keep going. First, distribute the t through the parentheses like this. Then use a property of exponents to write that like this, and I will do a little rearranging as well. Then say to yourself, e to the -2t, that's an exponential decay. That sounds good for a mass in a spring. Y being in position is it's decaying to 0. But what about that? Euler's identity, which allowed us to derive the most beautiful equation in the universe, that e to the I pi plus 1 is 0, and we derived Euler's identity from Taylor series, says e to the I 3t is cos 3t plus I sine 3t. Yes, we derived that with Taylor series, though that does beg questions like, is Taylor series valid with imaginary numbers, and can you rearrange Taylor series and all sorts of stuff like that? We sort of pushed that stuff under the rug and ignored subtle questions like that and said, hey, this is good enough for us. There are other ways to derive that these are equal, that are, you might say, more geometric and intuitive that way. We're just trusting it at the moment. Distribute this through the parentheses and get e to the -2t cos 3t plus I e to the -2t sine 3t. Now stare at this for a bit and think, I got a mass on a spring. There's some friction. If there were a lot of friction like we saw on Wednesday, the mass probably wouldn't oscillate. It would just slowly decay to 0 in position. If there's just a little bit of friction, it probably should still oscillate back and forth a bit, but with a smaller and smaller amplitude. That's what these functions do. Cosines and sines oscillate. They get multiplied by exponential decay. The amplitude's going to get smaller and smaller. The graphs of these functions individually, ignoring the I and ignoring the plus sign for that matter, are graphs that look like this, that go up and down, but decay to 0 as t gets larger. Maybe these two functions, which are regular real functions, solve the differential equation. Guess what? They do. Amazing. And I used complex numbers to figure it out and figure out what they are. Let's check that they solve the differential equation. I'll check that one of them does at least. Let's define f of t to be e to the -2t times cos 3t. What would it mean for this one to solve the differential equation? Here's the differential equation up here. It's got to mean its second derivative plus 4 times its first derivative plus 13 times the function must be always 0. Now, if I enter this, it may not be 0 right away. Maybe it will, maybe it won't be. It's not, but if I simplify, it's 0. In the unsimplified thing, do notice everything does cancel. Distribute the 4 through here. You get a -8 e to the -2t cos 3t would cancel with the +8 e to the -2t cos 3t, and a -12 e to the -2t sine 3t would cancel with the +12. So it's not a figment of your imagination to say it simplifies to 0. It does. For all t, it doesn't matter what t is. This is a solution of the differential equation. If you plot it, say over from 0 to 4 pi, we get some oscillations that are decaying to 0 pretty rapidly. In fact, they're hard to see after a certain point. Let's just go to pi. You can see it a little bit better there. They do continue to oscillate, though from an engineering perspective, mathematically it continues to oscillate slightly. From an engineering perspective, those oscillations are so small you don't even observe them, right? They're unobservable oscillations after a certain point. So effectively, it's become to rest. at a certain point. All right. So that's using complex numbers to find a couple solutions. These do happen to be, well, they're not scalar multiples of each other, so they are linearly independent, to use a term that I used on Wednesday. And they do turn out to span the solution space, meaning any solution is a linear combination of them. A general solution is y equals c1 e to the negative 2t cos 3t plus c2 e to the negative 2t sine 3t. Notice I did not put an I in here anywhere. The I, the imaginary unit, and the complex numbers was just to help me figure these things out. Not to actually use in the answer. Just help me figure out the answer. It was just a tool. Likewise, more generally in complex analysis, which again is being offered next spring, and if you take multi especially, you'll be prepared to take if you want to. In complex analysis, complex numbers and complex functions are all about developing tools that are pretty cool in their own right, but they do help you solve real problems. Real problems like this, real integrals as well. There's plenty of integrals complex analysis helps you solve that you can't really solve any other way. It's amazing. Can I think of one? I think maybe, for example, an integral like, I might be wrong about this, I'm just guessing. An integral like integral from 0 to infinity of sine of x over x turns out to equal pi over 2. And I don't think you can solve that really other way. I might be wrong. Like, is there a elementary antiderivative of this? I don't think so. Now, sine integral is all you get for the answer there. What is that? It's just a new function you've never heard of before. That's not what it is. But evidently it approaches pi over 2 as x goes to infinity. And that's something, this value here is something you can derive with complex analysis. Okay, so it's pretty cool. They are a cool tool. You can use general solutions to solve initial value problems. That's probably a bit too much work for us to put on the final exam. But you should understand the idea that if you've got two linearly independent solutions, you can write a linear combination of them to get a general solution. I could use initial conditions for the position and velocity to figure out C1 and C2. It's a lot of work. I'm not going to bother.